In this talk, I plan to tell you about several surprising connections between the study of suprema of stochastic processes, thresholds in probabilistic combinatorics and theoretical computer science, and the integrality gap of a broad and interesting class of integer linear programs. It turns out that all of them are connected via the lens of an optimization problem under randomness. So let me start by introducing this key optimization problem under randomness that we will focus on throughout the talk. In a general setup, we are given a finite set X. On a set X, we are given a collection of linear valuations lambda, which simply assigns to each element of X a non-negative real number. Now we will extend this valuation linearly to all subsets W of X, so the value lambda of W is simply the sum of the values lambda of X over all of the elements X in W. Now, we'll be interested in the function m of w, which is just the maximization over all valuations lambda in our given collection of valuations of the value lambda of w. So in theoretical computer science term, this function is simply a fractionally subadditive on XOS valuation. Now, what makes the situation interesting for us is the introduction of randomness. So we will take a random sparsification of the finite domain X, and we let XP be a random subset of X where each element is retained independently with probability P. And now the main question for us will be the following. What is the behavior of the random variable m of XP? So first, let me point out that understanding this random variable m of xp essentially entirely encapsulates the study of thresholds of monotone properties or monotone Boolean function. So first reminder, a property P over subsets of X is said to be monotone if whenever we have a set A in a property P and B is a superset of A, then B must also be in the property P. So of course, you can just think about a monotone property as a monotone Boolean function. Now, given a collection script H of subsets of X, let me denote by bracket of H the property over subsets of X that consist of the sets W, where W contains at least one of the sets H from the family script H. It is easy to see that bracket H is a monotone property, and we will conveniently use the simple observation that in fact any monotone property can be written in the form bracket H for a suitable family of sets script H. Now I will usually refer to the family of sets script H as the family of target sets or target structures. So now in the study of threshold, the threshold PC of H is defined as the value P for which the probability that the random subset XP is contained in the property bracket of script H is equal to 1/2. So now to make the connection between m of xp and the threshold, let me set up the following very natural uniform valuation. So for each set H in a target collection, let us consider lambda H, which simply equidistribute a total mass of 1 across all of the elements of the set H. Now, we can make a simple observation that the random set XP contains some set H from the target collection if and only if the maximum m of xp with respect to this uniform valuation lambda H is large. It's larger than 1 minus 1 over L, where L is the maximum size of a set H in the family script H. And so in particular, to understand the threshold PC of H is the same as understanding the event that m of xp is bigger than 1 minus 1 over L. Now, let me point out a very different, but also very interesting connection of m of xp, and now it is to the study of suprema of stochastic processes. So let's recall that the random variables that we have defined earlier, so lambda of xp, they are simply linear combination of independent Bernoulli P random variables. And now if we look at the collection of random variables lambda of xp, indexed by the valuation lambda in the given collection, this forms a stochastic process that we call a selector process. So in particular, the maximum m of xp is simply the maximum or the supremum of a selector process. Now, the study of suprema of stochastic processes is an important direction in probability theory with many influential applications to computer science, machine learning, statistics, and so on. And in the classical case of Gaussian processes, we now have a very good understanding of suprema of Gaussian processes thanks to many fundamental developments culminating in Talagrand's majorizing measures theorem. Now, beyond the Gaussian case, it's a challenging task, and Talagrand has a major program to characterize the suprema of general stochastic processes. In this context, it turns out that selector processes play a crucial role, so they can be used to simulate very general processes, such as general empirical processes. Let me also mention that in the past 10 years, there are wonderful breakthroughs in the study of chaining for the work of Bednorz and Latala, and then later extended by Talagrand, which tell us that essentially studying the suprema of general processes can be reduced to just the case of positive selector processes. And in positive selector processes are exactly the case of understanding the random variable m of xp in the exact setup that we have mentioned at the start of the talk. So in particular, one of the last missing piece in this picture is what we can say about suprema of positive selector processes, one of the important unfulfilled dreams of Talagrand. So now let us return to this main problem, which we'll now focus on throughout the talk. And let me note that what we really care about will be good general sufficient conditions that allow us to say that the maximum m of xp is large. However, let us first start by building up our intuition about the problem and first try to figure out what are some easy and natural obstructions that forces the maximum m of xp to be small. So first, let me make a convenient normalization assumption. So let me assume that for each of the valuations lambda, the total valuation lambda of x is equal to 1. So under this normalization, each of the random variable lambda of xp will be typically of order p, and which we consider to be a very small parameter that's going to 0. On the other hand, we can make also the easy observation that in this assumption, then of course, the maximum m of xp is always deterministically bounded above by 1. Okay, so now let me define a family of sets. Given any real number t, let me define ht as the union over all valuations lambda in our given collection of the collection of subsets w of x, where the valuation lambda of w exceeds the threshold t. So now, of course, m of xp is at least t if and only if the set xp is contained in the property bracket of ht. So in other words, if and only if xp contains some set h from this collection ht. So let me note that, of course, given the collection of valuations lambda and the parameter t, then this collection of sets ht is an entirely deterministic collection of subsets of x. Okay, so now to understand what are some natural and easy obstructions to this event that m of xp is at least t, then we can just turn to find obstructions to the event that xp is contained in bracket of ht. And our lessons from probabilistic combinatorics tell us that there are a very good broad class of obstructions that we should consider for events of the form xp is contained in bracket h. So towards that end, let me make an important definition. Given a family of sets script h, we say that h is p small if there exists a family of sets G with the following two properties. So the first property is that G covers H, which just means that every set from H must contain as a subset some set G from the collection script G. And the second property that we want is smallness, which means in this case that the sum over the sets in G of P raised to the size of that set have to be smaller than 1/2. Okay, so you can see that this smallness is really just standing for a naive union bound proxy. And so I will refer to any such small cover G of H as a naive union bound obstruction to the family of target sets H. And in particular, by the union bound, it is easy to see that whenever H is P small, then the probability that XP is contained in bracket H will have to be smaller than 1/2. Now, in particular, specializing to the family of sets HT that we have constructed, we then see that whenever HT is P small, then the submaximum M of XP cannot be large with a high probability. So in particular, M of XP is larger than T with a probability that is less than 1/2. Okay, now here comes the amazing insight of Talagrand. So Talagrand made a bold prediction that the naive union bound obstruction that we have considered is perhaps the only way in which the maximum M of XP can be small. So in particular, he poses the selector process conjecture, which can be equivalently stated in the following form. Let us consider the case where the family of set HT is not P-small. So the case where there is no naive union bound obstruction to the family of sets HT. Then there is some universal constant C, so that the probability that the maximum M of XP is at least C times T is at least C. So in particular, whenever the family HT is P small, then the probability that M of XP is larger than T have to be less than 1/2, and vice versa. Whenever HT is not P small, then M of XP is at least of order T with some positive constant probability. And if this result is true, then it would completely reduces the question of determining the order of the maximum M of XP to just the task of checking the P smallness of this deterministic collection of sets HT. Okay, so now let me remark that Talagrand selector process conjecture actually has many different, essentially equivalent reformulations, and each one of these statements carry a different meaning and impact. So let me go over a subset of these reformulations in the next few slides. So in fact, this one I want to mention because it was one of Talagrand's original formulation of the conjecture. So in this formulation, he conjectures that if we look at the tail event E, which consists of all of the subsets W of X, where the maximum M of W exceeds the expected value of M of XP by some large universal constant factor C, then this tail event E is going to be P small. So it will admit a naive union bound obstruction. So what is nice about this is that, well, of course, because E is a tail event, by Markov inequality, we know that the probability of the event E is small. But Talagrand is saying that for the tail event of the supremum of a selector process, we actually know a lot more. In particular, this tail event is very structured, and it is explicitly small in that this smallness can be certified by using only the very naive union bound. And Talagrand poses the conjecture in this form originally because it is in fact an exact analog of a result of Talagrand in the setting of suprema of Gaussian processes. Now, let me also mention another reformulation of the selector process conjecture, and this one is actually very useful for its proof. So in this formulation, we are given a family of target sets H, and we assume that H is not P-small, so there is no naive union bound obstruction for H. And so in some sense, you should think of the condition of being not P-small as a nice combinatorial condition about the sets in the family H, that they are not clustering too heavily around any small part of X. Now an adversary can come in, and the adversary is allowed to arbitrarily place a valuation lambda h for each set H in the target collection script H. And the only constraint to the adversary is that the valuation have to be supported on the set H, and it have to sum up to 1 in total. And the conclusion is that if we look at the expected value of the maximum M of XP with respect to these valuations lambda H, then this expected value have to be at least some universal constant C that is independent of P. So let me note why this statement is quite remarkable. Well, the only assumption that we make here really is the combinatorial assumption that the support of the valuations lambda H is not P small. And this assumption somehow turns out to be enough in order to guarantee that whenever we maximize over all of the sets H over all of the valuations lambda h that we are considering, the random variable lambda of xp, each of which have order only typically around order p, which can be extremely small. But as soon as we do the maximization over the set in H, then immediately we can guarantee that typically, at least in expected value, the maximum will be at least some universal constant independent of P. So in particular, it's very large. Okay, and this statement we can think of as a description this of behavior of fractionally subadditive functions under a random sparsification of the domain X. And it is very strong in that the only assumption that we need on the linear functions defining our fractionally subadditive valuation is that their support is not heavily clustered. Their support satisfies this nice condition of being not P-small. And in a sense, which we will return to later, we can also think about this statement as giving us quite precisely what is the correct phenomena, what is the correct description of what a random subset XP can capture. So now let me mention that earlier in joint work with Jin-Young Park, we resolved Talagrand selector process conjecture, and in particular, all of the previously mentioned equivalent formulations hold true. So in fact, in our work, we also consider a small extension. So we show that a similar result also holds in the setting of the positive empirical processes. And in later works by Bednorz, Martinek, and Meller have also extended the result to broader classes of stochastic processes. Okay, so now let me return to the study of thresholds of monotone property. That's one of the two motivations that I mentioned at the beginning of the talk. It turns out that in the study of threshold, two wonderful theoretical computer scientists and combinatorialists, Jeff Kahn and Gil Kalai, also made a very similar and bold prediction. So they also predicted that the naive union bound is perhaps the only obstruction to the emergence of structures in general random discrete system. And more precisely, the Kahn-Kalai conjecture says that whenever we are given a collection of target structures H, which is not P-small, so it doesn't have any union bound obstruction, then if we look at a random subset of X of density roughly P times log X, then this random subset will have to be contained in the property bracket H with probability at least 1/2. In earlier work with Jin-Young Park, we also resolved the Kahn-Kalai conjecture, in fact, in a slightly more precise form, where we can replace the factor of log X by the factor log L, where again, L is the maximum size of a set in the target collection script H. Now, earlier, we have made the connection between the random variable m of xp and the study of thresholds. So let's recall that connection. To make the connection, we will consider the uniform valuations. So for each set H, we'll consider the evaluation lambda H that simply equidistribute a total mass of 1 across all of the elements of H. And now under these uniform valuations, we can of course restate the Kahn-Kalai conjecture and a theorem that I proved with Jin-Young Park as saying that whenever we have a family of sets H, which is not P-small, then the maximum M of XCP log L will have to be very large, larger than 1 minus 1 over L, with probability at least 1/2. Okay. So written in this form, we can see quite clearly a connection between the Kahn-Kalai conjecture and Talagrand selector process conjecture. And in a sense, the Kahn-Kalai conjecture can be thought of as a uniform weight, but high accuracy analog of Talagrand selector process conjecture. And indeed, the proof of Talagrand selector process conjecture was an important precursor to the key idea behind the proof of the Kahn-Kalai conjecture. But let me remark that at this point, given the two results that we know, they are still not formally related, so we cannot use one result to formally derive the other. So now let me juxtapose the two results that we have discussed so far, the Kahn-Kalai conjecture and the selector process conjecture. And implicitly, we can see that both of them are really about the behavior of the random variable m of xq for some parameter q in the range of interest, which is between p and roughly p times log L. And let me note one very attractive feature of Talagrand selector process conjecture is that it tells us about an interesting and general phenomena that already hold at the level of the random subset xp. So we don't need to have the mysterious and in some sense quite hard to understand log factor that is required in the Kahn's-Cali conjecture. So of course, if we have some phenomena that already hold at the level of XP, it will give us more advantage and more leverage in using this phenomena for deriving other interesting conclusions. And now through the lens of M of XQ, we can then see that potentially we have a very rich landscape here that goes on the way between what we can observe at the level of XP and what we can observe at the level of XP log L. Still, let me remark that given the results that we know so far, we really only understand two specific points in this landscape, which is the endpoint when Q is equal to P of the Talagrand selector process conjecture, and the endpoint where Q is equal to roughly P times log L, that is in the Kahn's-Cali conjecture. Okay. So now that begs an obvious question. So can we optimally interpolate the phenomena between what we observe at XP and what we observe at XCP log L? So in particular, how does the random variable M of XQ behave for any Q in between this range of P and CP log L? So before getting to the description of the main result in this talk, let us consider one simple example that at least guide our intuition to what this correct behavior of M of XQ should be. So in this example, we will consider the graph set X as a rectangular board, and it has roughly n rows and around P inverse many columns. The family of target sets H will now consist of all transversal. So each set in H is a collection of elements, one per row. Now we will also consider just the uniform valuation. So lambda H will simply assign to each element of H a weight of 1 over n. Now we can observe that a row will have empty intersection with a random sample XPS. So here S is the parameter that ranges between 1 and roughly log L. Then a row will have empty intersection with XPS with probability at least around exponential in minus S. So in particular, with high probability, we can observe that there will be an exponential in minus S fraction of rows, which will be empty. And hence, with high probability, the maximum M of XPS will have to be at most 1 minus a quantity that is exponential in minus F. Okay, so this will now lead us to the following conjecture, which we term a sharp selector process conjecture. So it has a similar identical setup to the Talagrand selector process conjecture. We're given a collection of such H, which is not P small. And now for each set H in this collection, we are allowed to place an arbitrary valuation lambda H is supported on H, and it sums up to 1. Now the conclusion is that with high probability, so with probability at least 1/2, the maximum M of XPS will have to be at least 1 minus exponential in minus S, which is tied up to this constant C. Okay, and the main result in our work is a proof of this sharp selector process conjecture. So let me rephrase the result equivalently in a slightly different way. So in this language, in exactly the same setup, what we want to say is that we want to understand what sampling density Q do we need in order to guarantee that M of XQ is at least 1 minus delta, is at least a quantity that is very close to the trivial upper bound of 1. And the theorem says that it is sufficient to take the parameter Q, which is of order P times log of 1 over delta. So now let me make a few remarks around the sharp selector process conjecture. So first, this result immediately implies the Kahn's-Cali conjecture as a direct corollary. So we can just use the uniform weight valuations lambda H, and we can just take delta to be, for instance, 1 over 2L, where again, L is the maximum size of a set in target collection. Also, it gives us a strengthening of the selector process conjecture in the context of suprema of stochastic processes. So if you recall, the selector process conjecture tells us that if we look at a small tail event, so the event E, where the maximum exists is expected value by a large constant factor, then that event is CP small for some constant C. And turns out that with the sharp version of the selector process conjecture, we can associate the explicit structure to even large tail events of the suprema. So the event where M of W exceeds the expectation by only a factor 1 plus delta. And let me also note that the trade-off in this theorem is optimal. And as we saw before, the transversal example is a case where this trade-off is optimal, but in fact, we can observe this optimal trade-off in many different examples, let's say perfect matchings or Hamiltonian cycles. Okay, so next we will see one point application of this sharp version of the selector process conjecture. And in this application, it will be towards understanding the integrality gap of a class of integer linear programs that we term to be of some cover type. And these integer linear programs are motivated from the study of fractional expectation thresholds and expectation thresholds in the study of thresholds of monotone properties. And we will see in this result that it will require the full flexibility of the general weight lambda in the sharp selector process result. And this is also one result where it can show us why we can gain significant advantage if we can understand some phenomena that already holds at the level of xp or at the level of xq, where q is allowed to be a lot smaller than p times log L, which is the upper end of the interval and which is where the threshold we observed in the Kahn-Calais conjecture kicks in. Okay, so understanding the earlier points where we have already an interesting phenomena turns out to be very useful here. Okay, so let me now describe this application. As I said, it is towards a problem that is interesting in the context of the study of thresholds. So let's recall that given a family of target sets H, the threshold PC of H is defined as the value P for which the probability that XP contains at least one of the sets H from the target collection script H is equal to 1/2. And now, as we saw before, we have the naive union bound obstruction, which tells us that whenever H is P small, then the probability that XP is contained in bracket H have to be less than 1/2. And then equivalently, this is just saying that P have to be a lower bound to the true threshold PC of H. So now it's natural to define the expectation threshold, PE of H, as the largest lower bound that we can obtain on the threshold PC of H by considering only these naive union bound obstruction. So it is the largest value of P for which H is P small. And of course, we can now rephrase it as the largest P for which the optimal value of the following integer linear program ILPP is at most 1/2. And here, this integer linear program just captures exactly the P small condition. So we have the variables W of G that takes value in 0 or 1 for each subset G of X. So these variables just define a collection of subsets script G of 2 to the X. And now the cover condition is rephrased in terms of the second condition here, which tells us that for every set H from the collection script H, the sum over subsets G of H of the variables WG have to be at least 1. And what we want to optimize is the cost, which is just the sum over all subsets G of X of the variable WG times the weight P to the size of G. So now the Kahn-Calais conjecture can be equivalently rephrased as saying that the threshold PC is within a log X factor of the expectation threshold PE of H. Now, it doesn't seem immediately useful to us, even if we know the Kahn-Calais conjecture in this form, because if we want to determine the expectation threshold PE, then we have to solve this exponential size integer linear program ILP. And of course, then a natural idea here would be to consider a fractional relaxation of this integer linear program, which Talagrand already did in one of his papers. So Talagrand proposed the fractional relaxation of the integer linear program ILP, which we'll call LPP. And this will be exactly just the usual relaxation of the program ILP, where we now allow the variables WG to have values between 0 and 1. We'll now define the fractional expectation threshold PF as the largest value of P for which the optimal value of this fractionally relaxed program LP is at most 1/2. And let us call any feasible solution W to the program LP a fractional cover of H. So it's a fractional relaxation of the notion of cover. So now we have the trivial relationship. PF is at least PE, and also it's easy to see that PF is at most PC. So the Kahm-Clay conjecture would imply the following chain of relations about these quantities. And in particular, they are all within a log x factor of each other. But this result would only tell us that the gap between PF and PE is at most a factor of log x. Now here comes another bold and very interesting conjecture of Talagrand. He conjectures that at this level of generality, in fact, there is always at most only a constant factor gap between the fractional expectation threshold PF and the expectation threshold PE. So of course, this can be equivalently stated as follows. If we are given any collection of sets H that admits a fractional cover W with cost at most 1/2, then we can also round this fractional cover and find an integral cover G for H that is now small with respect to a parameter that is a constant times P. If this is true, it is a very remarkable instance where there's no integrality gap for this large natural class of ILPs, or for this large class of ILPs of a cover type. Now, progress towards this interesting conjecture of Talagrand has been limited to a few special cases. So in the original paper, Talagrand shows that this routing statement is true if we assume that the fractional cover W is supported on singletons, so sets of size 1. And only until very recently, it is shown that this routing statement is true for fractional covers W supported on sets of size 2. And already there, the argument is based on an explicit construction of the integral cover G based on the fractional cover W, and it's a fairly involved construction. Now, as an easy corollary of the sharp selector process conjecture, we can show that whenever we are given a family of sets H with a small fractional cover W supported on sets of size at most T, then we can also find an integral cover G for H, which is now small with respect to the parameter Cp over log T. So in particular, immediately for any bounded constant T, this result allows us to round any fractional cover W supported on sets of size bounded above by a constant, and show that the Talagrand's conjecture is true in all such cases. But furthermore, in a nice work of Fisher and Person, they consider a randomized routing procedure that can handle sets of large uniformity in the fractional cover, so sets of uniformity at least log x. So as a corollary, by combining our result with the randomized routing argument, we can obtain a much improved gap between the fractional and the expectation threshold. So in particular, PF is always within a log x factor of the expectation threshold PE. And let me note that up until our work, in general, the best gap between the fractional expectation threshold PF and the expectation threshold PE is still only a factor of log x that comes from the Kahm-Clay conjecture. So this immediately gives an exponential improvement over the best previous known gap. Okay, so now let me tell you just a little bit about how we can prove quickly this result on rounding fractional covers using the sharp selector process conjecture. And what's interesting is that in this result, which is implicitly about rounding a fractional cover, our argument is completely implicit. It is existential and not algorithmic. So in fact, the key, the only key input to allow for this routing procedure is the use of the sharp version of the selector process conjecture. Okay, so the first step, we will set up a natural collection of valuations lambda h. Roughly for each element x in h, this valuation will just be the normalized sum over all subsets S of h that contains the element x of the value under the fractional cover W, Ws. So now we will assume by contradiction that H does not have any integral cover, which is Cp over log T small. Now by the sharp selector process conjecture, we can obtain then that the maximum M of x C prime P for some constant C prime will have to be very large, will have to be at least 1 minus roughly 1 over 2T. So now by doing some algebra, we can just reorder this result to get the conclusion that typically, if we sum over all subsets S of a random sample XP of the weight under the fractional cover WS, then this will have to be large. But this will now be a direct contradiction to the fact that the fractional cover W is small, which tells us that the expected value of this quantity have to be small. Okay, so we see that for constant T in this result, it is very important that we understand the phenomena that we have the sharp selector process conjecture already for a sample of a subset of X with density only a log T factor, so a constant factor larger than the parameter P over log T, which is the smallest parameter considered in this picture. Okay, so with that, let me very briefly just tell you about some of the main ideas behind the proof of the sharp selector process conjecture. Turns out that the proof of this result is significantly harder than the proof of both the Kankali conjecture and Talagrand selector process conjecture. But still, it follows from a similar general high-level philosophy. So let me mention that in the previous two cases, the Kankali conjecture and Talagrand selector process conjecture, the general approach looks somewhat like the following. So in the key step, we will identify the key notion of the minimum fragment, so that each minimum fragment T will be born based on the interaction of a set H in the target collection and a subset W, which you can think of as a random subset of X. And this minimum fragment T is defined so that the set Z of H and W, which is defined as a union of W, and this minimum fragment T of H and W, has satisfied certain nice feasibility condition that allows us to say that whenever W is a bad set, if whenever W doesn't have some property that we want, let's say M of W is less than 1 minus delta, then there is some contrast between Z and W that allows us to efficiently encode the set T as a subset of Z. And in particular, we want to encode T as a large subset of some structured subset I of Z, which can be determined purely based on the knowledge of the set Z. And if we can achieve these two conditions, then we can deduce small cover for the family of sets H, and this cover will just be constructed based on the fragment T of H and W. So in the case of the Kankali conjecture, we will just define T to be the minimal subset of H so that the set Z, which is the union of W and T, satisfies a simple feasibility condition, that is that Z have to be contained in the property bracket H. And of course, for us, we care about the case where we say that W is bad whenever W doesn't have this property that we want. So W is not contained in bracket H. So we can use this contrast between W and Z in order to efficiently identify this fragment T of H and W inside the set Z. And the last key idea in the proof of the Kankali conjecture is that we then need to iterate this procedure a logarithmic number of times. So in the case of Talagrand selector process conjecture, the overall scheme is fairly similar. So we'll let T be minimal subsets of H so that the union Z, which is the union of W and T, satisfies certain important feasibility condition. And now this feasibility condition, as I mentioned, will need to be defined appropriately so that we can efficiently identify the set T inside Z whenever M of Z is large and M of W is small. So this is really the most tricky part of the argument. It is to correctly identify the right feasibility condition for Z, and it's a fairly involved condition in our work, involves defining the correct penalty term. But nevertheless, once you have the correct feasibility condition, then the rest of the argument follows from the recipe in the general approach. So one key feature of the proof of Talagrand selector process conjecture is that we cannot iterate the proof of the Talagrand selector process conjecture. So in defining the right feasibility condition, the fragment T of H and W must ignore certain elements, and it just inhibits the iteration that we saw in the Cantelli conjecture. And in a sense, this iteration is exactly what we need in order to prove the sharp selector process conjecture. So in the end, in the proof of the sharp selector process conjecture, we need to devise a new idea, which we call a tower of minimum fragments. It is essentially a folding of the entire iteration into the definition of the minimum fragment. And again, the key and most involved part of the proof is to design the correct feasibility condition for the set Z. We are a union of random samples Wi and the fragments Ti within the tower of minimal fragment in order so that we can efficiently encode the family of sets Ti. And this turns out to be very challenging and requires a very delicate definition of feasibility. So for the full detail, I invite you to read the full version of the paper. So with that, let me conclude. We thought that our main result is about a sharp understanding of the random variable m of xq for q in between the interesting range of p and p log L. So we optimally interpolate the phenomena between Talagrand selector process conjecture and the Cantelli conjecture. And we saw that understanding this sharp phenomena already for parameter q that is allowed to get very close to p is very important in our application to Browning fractional covers, so to the integrality gap of these integer linear programs that arise in the study of expectation thresholds. And we then obtain an exponential improvement on the integrality gap between the fractional and the integral expectation thresholds. We also saw that the key idea behind the proof is a strengthening of the concept of the minimum fragments that was crucial in the proof of the Cantelli and Talagrand selector process conjecture. And so here we need to work with the tower of minimum fragments. But in general, this framework around the minimum fragments allow us to have a unifying perspective on a variety of situations concerning thresholds or concerning sunflowers in set systems and so on. And let me also mention that there are many new emerging connections between this study and other topics of interest, such as hypergraph container. On the other hand, there are still many interesting questions that remain to be explored. And so one of which comes from the study of suprema of stochastic processes, I state here, is a beautiful conjecture and a beautiful principle of Talagrand, so Talagrand solid convex horn principle. And really, for these types of questions, what we want is to get a more explicit characterization of the p-smallness of the families of sets HT that we have constructed earlier, which play a crucial role in the Talagrand selector process conjecture or in the study of suprema of selector processes. And in a sense, yeah, these more explicit characterization of p-smallness for the sets HT would be very useful in application. Thank you.